This is project 3, video number 1. I've done some preliminary work. We're supposed to generate this graph, the graph of position versus time, by means of a MATLAB function, or write a MATLAB function that'll produce that graph. And these are the results from the test, where I've got the velocity for the motion described. I start with that. That's the easy one to get down. And then I define these special times, the 0, 5 seconds, 10 seconds, 15 seconds, where things started or ended or changed. So in particular where the velocity underwent, or the acceleration underwent an abrupt change at 5 and 10 seconds. So I got time intervals t0, or times, instants in time, t0, t1, and t2, and t3. And then for the time interval from 0 to 5 seconds, I've calculated the acceleration. I call that a sub 0, 1. And I have to do the algebraic solution, everything in terms of symbols first. So I got it the change in velocity from during the 0 to 1 time interval, time 0 to time t1, or time t0 to t1. And the velocity I define as v0 at the start of that interval, v1 at the end of it. So the acceleration is calculated right there, and I do the same thing for the 1 to 2 interval. The 1 to 2 interval, actually, I don't do the same thing. By inspection is 0 because the velocity is constant. And then I do the same thing as I did for the first interval, time interval for that third time interval. Work everything out algebraically first, and then substitute the values with the units. So I've got accelerations during each of the time intervals. And now I want to generate a function that gives me the position as a function of time on each of these 3 time intervals. I'll do that separately. So for the first time interval, we can use the idea that x, I think I'll work in blue here, x is equal to x0 plus v0 times t plus 1/2 at squared. And then we got to doctor that up for our specific purposes. X on the interval 0 to 1, I'll leave that alone. x0 is good, v0 is good, t1 is good. It's just this one, so it'll be the acceleration on the time interval from 0 to 1. And that's what I've got to evaluate, where everything's known. So in order to fill up an array from time 0 to time t1, I'll be using this formula. So I think I'm going to need that in my code outline, so I'll call that 1. And I'm also going to need, for figuring out where things are during the next time interval, I'm going to need the position of the car at time t1. So I'll go ahead and solve for that. That'll be x0 plus v0 times t1. So t1 is 5 seconds. I'll be plugging that in. I mean, this function I'll be using values of t from 0 to 5 seconds. But plus 1/2 a01 times t1 squared. So let's find out where it is at the 5 second mark. So it started out at minus 15 meters. It was 15 meters behind the start line to start with. Started out with a positive 15 meters per second velocity. Time t1 is at 5 seconds. And then plus 1/2. The a01 I found to be 5 meters per second squared. Then times 5 seconds quantity squared. So at time t1, namely at 5 seconds, I find the position to be 122.5 meters. Alright, so that's going to be a useful value. And then for the second time interval, I'll say x. This was from t0 to t1, t0 up to t1. So this is from t1 to t2, and I'm going to say the x is equal to wherever it was at time t1 plus v1. The velocity is constant during that time interval, so I could use v1, the velocity corresponding to time t1, or I could use v2. I'm going to use v1. Might as well write it on the graph here too. v1 40 meters per second, and v2 is equal to 40 meters per second as well. So down here in my calculation, I think I use v1, and then it's just v1 times the amount of time that has elapsed since time t1, so it'll be t minus t1. So at time t1, so this is good from t1 to t2. At time t1, this will be 0, so x will just be equal to x1, just what we found up here. And then at later times, say at time t is equal to 6 seconds, this will be 6 seconds minus 5 seconds, 1 second, times that constant velocity plus wherever it was at time t1. So that'll be good. We're going to need that in our code, so I'll call that equation 2, and then from t2 to t3, we've got x is going to be equal to wherever it was at time 2. So I better evaluate that to find out what that is. So it follows that x2 is equal to x1 plus v1 times t2 minus t1, which is equal to 122.5 I think I'll go down to the next slide on that. 122.5 meters plus v1 is 40 meters per second times t2 is 10 seconds minus t1, which is 5 seconds. So x2 is 322.5 meters. Alrighty. This is x2. And then from 2 to 3 starts at x2 plus whatever the velocity is at time 2 times how much time has elapsed since time t2, which will be t minus t2 plus 1/2 a 2 to 3 times t minus t2 quantity squared, the amount of time that's elapsed since time t2. Alright, and that should do it. result. I should make a check. T2 is 10 seconds. When t is equal to 15 seconds, this will be 5 seconds. This difference in times will be 5 seconds. So if I evaluate that for x2 is 322.5, if I evaluate that whole thing, I should get 0. So I'm going to go ahead and make a quick check on that and see if I actually get 0. And of course I'm wrong about that. It's the velocity that comes down to 0, not the position. So let's go ahead. We'll put this down. It's not going to be needed in calculating anything, but it'll be a nice check on our graph. So this will be x3 is going to be equal to x2 plus v2 times t3 minus t2 plus 1/2 a23 times t3 minus t2 squared. And so x3 is equal to 322.5 meters plus 40 meters per second times 15 seconds minus 10 seconds plus 1/2 minus 8 meters per second squared times 15 seconds minus 10 seconds quantity squared. And I evaluate that, I get 422.5 meters. So again, that'll just be a check on the graph. It should wind up at 422.5 meters, not 0 like I said a few seconds ago. That was just wrong. Alrighty, I think we got enough to code this up. So I'm going to go we have no input variables, so we can initialize some variables. X, we got x0, yeah, everything that we have in here, x0, v0, and a01. x0, v0, a01. That just means initialize, means just set those variables. So code outline. Set those quantities to their given values. So x0 is minus 15 meters, v0 minus plus 15. I think I'll just call it 15. 15 meters per second. A01, that was calculated, but I'll just type that into the computer code. Then x1, v1, and we didn't have an a12. It was just 0, so I don't need to initialize anything there. I don't have it included in the formula up here. I could have had a plus 1/2 a1 times that time difference squared, but a1 to 2, but that's just 0. So x1, I did get a value of it, 122. I'm going to plug that in there. I'll just use the pencil and paper part of that. v1 is 40 meters per second that was given. And then we got x2, v2 and A2 to 3. X2 we had a value for 322.5 meters. V2, that was 40 meters per second as well. Remember, it was constant from time 1 to time 2, from T1 to T2, so 40 meters per second, and this we calculated to be 8 meters per second squared. Alright, so that'll be step 1. Step 2, evaluate. I need the times as well, so T1 equals T0. Do I have a T0 in any of these equations? No. For this first part, I used the fact that T0 was 0, so instead of having T1 minus T0, I just have T1. So let's go. T1 equals 5 seconds, T2 equals 10 seconds, and T3 equals 15 seconds. Evaluate. I think I gotta set up some time arrays. So set T0 to 5 seconds equal linspace 0, 5, 100. So initialize, this will be an array, T from 0 to 5 seconds, and then I'll put 100 values in there. That's probably going to be overkill for keeping things smooth, but I don't think it'll take too long to run the code anyway. And then T 0, I'm going to cross my zeros so they don't look like O's. To, and it wasn't 0. It's I want to go 5 to 10. So 5 to 10 seconds equals linspace. There you go, 5. I'm actually going to make that 101. I'm going to make it so it goes in steps of 100th of a second. It has to do with the fact that I got to assign the 0 one takes up a little bit. Like if you go just from 1 to 5, that would be 5 elements, but from 0 to 5, that would be 6 elements, so 1 more than you might think you need. So this will go 5, 10, go 101 as well. It'll take me up to 10 seconds, and then T 15 to 10 to 15. 10 to 15 seconds is equal to linspace of 10 to 15 and 101 values in there. And then I'm going to evaluate eval equation. I think it's 1. So yeah, it goes 1, 2, and 3. Equation 1 using T equals T10 to T0 to 5 seconds. So put the result in, I'll go x 0, and I'll go ahead and say store result. Store result. And I'll call it x0 to 5 seconds. So that'll give me the values of x from time 0 to 5 seconds. These next two steps are going to be the same. Just copy that down with minor differences. Almost the same, I should say. Eval equation 2 using t equals t5 to 10 seconds. Store result in x5 to 10 seconds, and then evaluate equation 3 using t is equal to t10 to 15 seconds, and store the result in x10 to 15 seconds. So now I got 300 values of x stored in 3 different arrays, 100 each, 101 each. It's actually 301 values, 303 values, and I had 303 times. So I'm going to put step 6. I want to put all the time values in one array. I'll go all. I use capital letter for all, so it doesn't look like tall. I guess it does anyway, but still. T all is going to be the array that I get when I put all 3 of these together. So T0 to 5 seconds, comma, T5 to 10 seconds, comma, T10 to 15. I've been consistent about crossing these zeros. So they look like zeros rather than, oops, not that one, rather than O's. That one was an O. Okay, I think I got them. So there's TO, and I'll go XO is equal to, it's going to be the same thing, except it all starts off with an X. Alright, and then plot T all, comma, X all. Then I'll create a plot of X all versus T all. And that should do it. So let's call that a wrap for project 3 video number 1.